Black holes, the universe's most enigmatic wonders, tease us with their dark and mysterious allure. These celestial bodies, cloaked in an inky shroud of obscurity, have intrigued astronomers and laymen alike for centuries. The key to their mystique? The event horizon, a boundary so formidable it traps everything, even light itself. This veil of darkness, once crossed, offers no return, marking the outer limit of a black hole's gravitational grip. Now imagine peering beyond this boundary, diving headfirst into this cosmic abyss. Thanks to the tireless work of astrophysicists Jeremy Schnittman and Brian Powell, this is no longer a mere fantasy. Using NASA's Discover supercomputer, they've created an immersive visualization that lets us plunge into the event horizon, offering a glimpse into the heart of a black hole. Today we journey into the heart of a supermassive black hole, just like one at the center of our Milky Way galaxy, through NASA's simulation. Imagine being 400 million miles away from a black hole, seeing dramatic distortions in space-time. Now picture yourself approaching this cosmic enigma. The sight that greets you is nothing short of spectacular. The surrounding accretion disk, a swirling mass of hot gas, and the background stars appear significantly warped. It's like peering into a funhouse mirror where reality bends and twists before your very eyes. As you draw closer, the intensity of the spectacle amplifies. The light from the stars and the swirling disk of gas around the black hole brighten, akin to a race car's roar growing louder as it speeds past you. This increase in brightness is not a mere illusion but a phenomenon known as gravitational lensing, where the black hole's immense gravity bends light around it, creating a mesmerizing show of celestial fireworks. Gradually, the journey starts to feel like an eternal descent. You are nearing the event horizon, the black hole's point of no return, beyond which nothing, not even light, can escape. But an intriguing cosmic trick is at play here. As you inch closer, time appears to slow down. It's as if the universe is holding its breath, making it seem like you never quite reach the event horizon. This bizarre effect is due to time dilation, a mind-boggling consequence of Einstein's theory of relativity. The closer you get to the black hole, the slower time appears to pass for you, compared to someone far away. It's as if you're caught in a cosmic slow-motion replay, with every second stretching out into infinity. As we journey further into the heart of the black hole, the laws of physics as we know them start to warp and twist, much like the space around us. The closer we get, the stranger things become, and the more we realize that black holes are not just objects in space, but cosmic laboratories where the fabric of reality itself is tested to its limits. As we inch closer, time seems to slow down, making it appear as if we never reach the event horizon. But this is just the beginning. The real adventure awaits us beyond this boundary, into the unknown depths of the black hole. Now, we teeter on the edge of the event horizon, the point of no return. This is where our journey through the black hole takes a thrilling turn. Picture this. We have two possible outcomes for NASA's camera, which has been our eyes and ears in this cosmic adventure. It either narrowly misses the event horizon or it crosses over it. Each outcome unveils a different facet of the black hole's mysterious nature. Let's start with the scenario where the camera crosses the event horizon. Once it crosses this boundary, it's in for a wild ride. The camera, much like any object in this position, undergoes an incredible transformation known as spaghettification. This is no ordinary pasta-making process. The intense gravitational forces close to the black hole pull on the camera so strongly that it stretches and tears apart. This happens in a fleeting 12.8 seconds. It's like a cosmic roller coaster, but instead of looping around, it's a one-way trip towards the heart of the black hole. This heart is the black hole's core, a point of unimaginable density known as the singularity. Here, all the rules of space and time as we know them come to a screeching halt. It's like stepping into another universe where the laws of physics are turned on their head. But what if the camera misses the event horizon? Well, it continues to orbit close to the black hole, caught in its gravitational pull but not quite crossing the boundary. In this scenario, the camera gets a front row seat to the strange effects of time dilation, where time seems to stretch and slow down, but we'll dive into that in the next scene. Whether the camera crosses the event horizon or just skirts around it, each outcome provides us with valuable insights into the enigmatic nature of black holes. In a blink of 12.8 seconds, the camera could be stretched and torn apart by the immense gravitational forces. Yet it's a small price to pay for the secrets we stand to uncover. In an alternate scenario where we orbit close to the event horizon without crossing it, time starts to behave oddly. This is where we encounter the fascinating concept of time dilation, a mind-bending effect predicted by Albert Einstein's theory of general relativity. To comprehend this, imagine you're an astronaut in a spacecraft orbiting near the black hole's event horizon. For you, on board the spacecraft, time ticks away as per usual. Your watch is ticking, your heart is beating, and you're aging at the same pace you would back on Earth. However, for your colleagues observing you from a safe distance away, something peculiar happens. Time, as they perceive it on your spacecraft, appears to slow down. Your watch seems to tick slower, your heart appears to beat less frequently, and you seem to age at a slower pace than they do. This phenomenon is known as time dilation. It's as if the intense gravity of the black hole is pulling not just on physical matter, but on time itself, stretching it, dilating it. The closer you are to the event horizon, the stronger this effect. So, while you might spend what feels like a few hours orbiting near the black hole, years or even decades might pass for your colleagues far away. This is not a mere trick of perception or an optical illusion, it's a real physical effect of the warped space-time around a black hole. The implications are profound. Imagine, if you will, an astronaut brave enough to venture close to a black hole, spending what feels like a few years in its vicinity, and then returning to Earth. This astronaut would find the world drastically changed. Their colleagues who had stayed safely back on Earth would have aged decades in what felt like just a few years for the astronaut. Returning from this journey, the astronaut would be younger than their colleagues who stayed far from the black hole. This is the strange and fascinating world of black holes and time dilation. The journey into a black hole, as seen through NASA's simulation, is indeed a thrilling exploration. Our cosmic voyage starts from 400 million miles away, where we first encounter the dramatic distortions in space-time. As we draw closer, the light from stars and the swirling disk of hot gas around the black hole intensify, akin to the roar of a race car growing louder as it speeds past. The journey, although appearing to take forever to reach the event horizon, is a mere 3 hours in reality. As we edge closer, we seem to slow down, and to an external observer, it appears as though we've stopped altogether. Now, here's where the journey takes a turn for the extraordinary. Our camera, our eyes into this cosmic wonder, can either narrowly miss the event horizon or cross over this boundary. In the first scenario, it's a close encounter of the black hole kind, where we get an up-close view of the event horizon without crossing it. However, should we cross the boundary, the camera undergoes a dramatic transformation known as spaghettification. The intense gravitational forces near the black hole pull on the camera so strongly that it gets stretched and torn apart within 12.8 seconds, spiraling towards the black hole's core, the singularity. Alternatively, if the camera orbits close to the event horizon but does not cross it, time begins to act in mysterious ways. It stretches, it dilates. For the astronaut on the camera, time ticks away as usual, but for those watching from afar, time appears to slow down. This time dilation effect means that when the astronaut returns, they will actually be younger than their colleagues who stayed far from the black hole. Such an expedition, though currently beyond our reach, offers a fascinating glimpse into the mysteries of our universe, with black holes being one of the most captivating phenomena out there.